In this video, we are talking about contest. Contest is a big topic. Here we just introduce some basic concepts, study some typical models, and then have a look forward. Let's start from an online version of contest, the crowdsourcing. Crowdsourcing is an internet service which solicits solutions to certain tasks by setting up some prizes. The task can be art design, software development, or even searching for something in a big area, and the prize can be monetary or in-kind reward. Like crowdsourcing, many online activities are using contest mechanism. We can conclude the main idea of contest simply as a competition toward prize. Here we have the formal definition of contest given by some scientists. And contest theory is a set of theories developed to achieve a better understanding and informed design of contest. A central question in contest theory is how to maximize a desired objective by allocating the prize in a proper way. Usually, the objective is the utility of production. We will discuss this later with different models. The research on contest-related topics has been carried out by scientists from different fields since the beginning of last century. Game theory models of contests are studied with auction theory, economic theory, as well as theoretical biology. Using compensation schemes on ordinal ranking has been studied by economists. Game theory with computational questions was studied by computer scientists. We now introduce some basic elements of a contest model under standard game theory framework. The agent, or we can call them participants or players. We assume that the agents are rational and strategic. They invest effort with a selfish goal to maximize their individual payoffs. The organizer, who arranged the contest, is expecting maximum utilitative production from the agent. This is a payoff function. In this function, S is the payoff, B is the effort, V is the skill parameter, X is the price, and C the production cost. The basic idea is we calculate the payoff by subtracting the cost from price. Effort, total effort, and maximum individual effort in a game are usually studied as a measurement of the utility of production. We also focus on how an agent invests the effort. During the investment, an agent can specify a value according to pure strategy or a probability distribution according to a mixed strategy. Similarly, we can define pure strategy Nash equilibrium and mixed strategy Nash equilibrium, when both agents cannot increase their payoffs by selecting another strategy. Skill. The larger the value of a player's skill parameter, the more proficient is the player. If an agent knows exactly who is going to participate in the contest and the value of their skill parameter, we say the game is with complete information. Otherwise, the game is with incomplete information. Prize. The prize allocation mechanism varies between games. Some prize items are indivisible. The competitors need to share them, while others can be divided in proportion to the effort. Cost. The production cost per unit effort can be constant, decreasing, or increasing.
Firstly, we explore games that model a single contest amongst two or more players. Such contests allow us to study situations in which players have no outside options, such as investing efforts in an alternative contest. The most basic type is known as a standard all-pay contest. These contests use a prize allocation mechanism that allocates the entire prize budget to the highest effort player. This type of allocation is commonly referred to as perfect discrimination, as it assumes a perfect identification of the highest effort player. There are different properties of standard all-pay contests, depending on the information known by the players. A game with complete information does not have a pure strategy Nash equilibrium. However, the game does always have one or more mixed strategy Nash equilibria. If there is more than one equilibrium, they are said to be payoff equivalent. Another property is the so-called exclusion principle. which refers to the exclusion of some players in order to increase the expected total effort. In some instances, it can actually be beneficial to exclude the highest skilled player, as this can result in more intense competition. A game with incomplete information has a unique symmetric Bayes-Nash equilibrium, in which players play identical strategies. The expected total effort is equal to the expected value of the second highest skilled player. Interestingly, the expected maximum individual effort is at least half of the expected total effort. Rank order allocations split prizes amongst 2 or more positions, usually as first, second and third place. This raises the question of how to split the prize in accordance with the given objective. If the given objective is to maximize the expected total effort in a game with incomplete information, it is optimal to allocate the entire prize budget to the first place. This also holds for a game with complete information, under the assumption that players have identical skills and decreasing marginal production costs. However, if the skills of players have non-identical prize distributions, there are instances where it is profitable to split the prize budget over 2 or more positions. In this case, assuming a game has 3 players, 1 high skilled and 2 low skilled, and each player incurs unit marginal production cost, the game will have a mixed strategy equilibrium, such that both the low skilled players will play symmetric strategies. Therefore, the more balanced the split between the 2 positions, the larger the expected total effort. Researchers have recently established a characterization for the optimal prize allocation for the objective of maximizing the expected maximum individual effort. This is known as a smooth allocation of prizes. This mechanism has a positive bias towards players who invest high effort, but does not guarantee the prize is allocated to the highest effort player. Therefore, this mechanism is considered to use imperfect discrimination. Smooth allocation of prizes can arise due to various factors. Firstly, the stochasticity of production, where individual production outputs are considered random and positively correlated with invested efforts. And secondly, the allocation of prizes are based on a ranking of players derived from noisy observations of individual performance outputs. Some examples of smooth allocation of prizes include proportional allocation, where the prize is split proportional to the agent's invested efforts, on the condition that at least 1 player has invested efforts, otherwise the prize is split. Secondly is the general legit allocation, which is a more general class of smooth allocation and allocates in proportion to an increasing positive valued function of invested effort. And lastly is the Tulloch allocation, which is a special case where the prize is allocated in proportion to a power function of invested effort with a positive exponent parameter, usually denoted as R. In general, the larger the value of R, the larger the share of prize is allocated to the highest effort player. Unlike standard all-pay contest, a game with proportional allocation has a pure strategy Nash equilibrium, which is considered unique. As opposed to single contests, multiple contests can often run simultaneously, for example crowd-serving services. These contests provide players with alternative options to invest efforts, which can have a significant effect on the effort invested in any given contest. Examples of simultaneous contests include simultaneous standard all-pay contest. During such a game, strategic decision-making consists of 2 components: choosing which contest to invest effort and deciding how much effort to invest. This decision is formed by the available information, such as the values of prizes offered. For instances of games with incomplete information, segregation is used. This is where players of a similar skill level choose contests according to identical mixed strategies. For example, a player with a higher skill level chooses a contest that offers a higher prize. Another type of production cost is where each player is endowed with an effort budget that he or she can split arbitrarily over available contests, similar to the Colonel Blotto game. Simultaneous contests can sometimes result in the sharing of the utility of production. For example, some online services rely on user-generated content, such as questions and answers in online Q&A services. Local utility sharing mechanisms are an example of such a mechanism where priority fixed shares of the utility production are allocated in decreasing order of individual contributions. Veta came up with the notion of monotone valid utility games. This is where players' payoffs are according to utility functions whose sum is less than or equal to the value of the social utility function. In addition, the following 2 conditions must hold: monotonicity condition, which restricts to social utility functions whose value cannot increase by a player opting out of participation, and marginal contribution condition, which restricts each player's utility to be at least as large as their marginal contribution to the social utility. Finally, a variety of games model contests with elements of sequential play. Architecture for sequential contests come in the form of single elimination tournaments. A typical single elimination tournament consists of 2-player contests and is defined by a binary tree and a seeding of players. Each contest of the tournament has one winner, and all the players that lose in the contest are eliminated from further competition. The winner of the tournament is the player who wins all the contests in which they participated.
With the accessibility of online competitions, an important element for contest is the use of a skill rating system, which provides a rating of players' skills based on observed outcomes. The most general approach of this system is to apply a numeric value to all contestants that results in an ordered list of participants by decreasing order. This is common in many full ranking systems such as league tables, leaderboards, or tournament seedings, where participants are listed based on their performance. Other uses may allow prediction of contest outcomes, primarily used in many online gaming platforms to predict individual skill parameters used for equally matching skilled players to provide different outcomes for the matches. However, the main challenges for this design is to accurately estimate players' skills based on sparse input data that contains information about contest outcomes. The skill rating system design is based on a statistical model of ranking outcomes, where comparisons of individual results is commonly used to be able to provide a basic measurement of individuals' performance. Generally, the system uses few parameters to represent the agent's skill ratings, such as the value for the individual skill and an extra parameter for the uncertainty of an estimate. Individuals are given performance random variables, assumed to be independent across different individuals and comparisons. Ranking outcomes is assumed to be in a decreasing order of individual performance, which is equal to a deterministic skill parameter, which is unknown and must be inferred from the observed ranking outcomes, plus a zero mean noise random variable, assumed to be from a Gaussian distribution and is independent for different individuals and comparisons. The result gives the ranking outcome that allows us to compare which individual has a higher skill rating, with the higher ranking being assigned to the individual with the higher rating. Additionally, we can also identify a probability that individuals will be higher with a comparison. One of the more common methods is the Firstone method, based on the work by Lewis Firstone, which assumes our random variable follows a Gaussian distribution, where we get a probability outcome based on two individuals using the given formula. Another model is the Bradley-Terry model from the works of Ralph Bradley and Milton Terry, related to the Firstone model that simply applies a frequency probability based on the individual skill parameters with the following formula. Finally, from our resulting ranking outcomes, we choose the statistical inference methods for the skill parameters from the observed outcomes, where we will be able to test hypotheses to evaluate our population. There are two common approaches. The first method is a frequentist inference that draws conclusions from the data based on the frequency or proportion of the data, similar to a maximum likelihood method, and is dependent on a distribution of the data. In this method, we consider skill parameters to be fixed but unknown, so that are not treated as random, and estimated by minimizing a given loss function. Second method is a Bayesian inference, which is a method of statistical inference using Bayes' theorem to update the probability of a hypothesis of each possible value of a parameter when more information is introduced. This defines a probability distribution over the possible values of the mean and uses sample data to update the distribution. Any newly collected data makes the distribution narrower around the parameter's true unknown value. Our skill parameters are set as random variables with a given prior distribution and amount to computing the posterior distribution of the random variables, conditional on observed ranking outcomes. Both methods differ in the set parameters but result in a similar outcome. The process will result in estimations of the skill parameters in the contest and allow us to draw conclusions about populations or hypotheses from the data. Contest theory encompasses scientific methods and theories for the better understanding and informed design of contests, with its goal to provide a contest designer with a set of theoretical results and methods that can be used for the design of a contest. This is a challenging task, primarily because of the complexity of user behavior and incentives that play a key role in most systems of concern. This topic expands into many additional areas on contest and game theory that will not be covered in this video, such as the ranking methods, with the problems of ranking alternatives and aggregation. several of the challenges in contest theory still remains open, as there are a number of additional factors to consider in the study. Hope you enjoyed, and thank you for watching.